Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about low-rank approximations, um, and we're also going to be talking about SVD and ID, and I'll explain more what exactly are those in a bit. So let's start with low-rank approximations. So we're gonna let A be some matrix. Um, so this is a 3 by 2 matrix, 3 rows and 2 columns. And we can actually decompose this into 1 row and 1 column vector. So we can decompose this matrix into 1 row and 1 column vector, right? So we can do that. Well, how do we do that? Well, let's say we have A here. Well, this is just going to be 1, 2, 3, 1, 1, and we're done, right? And so this is the basis of rows of A, right? How do I know I got it correctly? Well, I multiply these two things together, right? So I get 1 times 1, that's 1. 1 times 1, that's 1. 2 times 1, that's 2. 2 times 1, that's 2. 3 times 1, that's 3. 3 times 1, that's it. So that's the basis of the rows, while this is the basis of the columns, right? Okay. And so similarly, let me do another example. If we say A is 1, 2, 3, 4, 5, 6, that matrix with those elements. Oh, my bad. 1, 2, 3, 2, 4, 6. Well, here we just say that's 1, 2, 3. Then we have 1, 2, right? And if, let's say, U is equal to this column vector, and we say, let's assign V to be the row vector. Well, A will then become something new. 1, 1, U, 2U, 1, 1. Now I'm also asking, it's not just U. Where did I get the U and the 2U? So where did that happen? Well, here we see that uh, I mean, we can try to compute for this thing. But you kind of, hmm, Brett, Brett, Bryce, Bryce was the fun. Okay, let me just say that's true for now. And then this is going to be something in terms of V. This is a 3. Okay, and then V here, what's that supposed to mean? Okay, let me actually check what I'm looking at. Because I also find this a bit weird. Like, where did these values come from? Like, they were so out of the blue. I'm just gonna check. Oh, it's an outer product. Okay. Yeah, so it's an outer product of U and V. Oh, so U builds the columns and V builds the rows. So that's what's happening. Okay. So U builds the columns and V here builds the rows, right? How is that possible? Well, okay, so basically it's the outer product of these two vectors. U is the column vector and V is the row vector. And so if we get their outer product, meaning we transpose V, well then we get the same A matrix. And here it says that U, is this V? I'm not super sure. It says here V builds the rows, and that's because each row of the resulting matrix A is a multiple of V, right? So each result of matrix A is a multiple of V. So 2, 4, 6, 1, 2, 3. And so that's why it builds the rows. And U, on the other hand, builds the columns because each column of A is a multiple of U, right? Each column on A, so we're talking about each column, is the same multiple of U, right? And so this would be again, well, U and 2U, and here you have 1 and 1 again, right? And so basically, this shows that, well, let me just look at it. Oh, wait. This shows that it's rank 1. Or let's look at this example. This shows rank 1. Why is that? We have one column and we have one row. That means it's rank 1. And because we have one of each. Okay, let me just go through another example here. Well, what if we say my A matrix becomes something else? 1, 2, 3 plus 10 to the negative 16. Then we do the same thing. Well, now we cannot find a U and V, right? So cannot find U and V. Such that A is equal to multiplying those two, right? But we can actually see something. So we can see in particular, that my A matrix could be divided. I could get this, and then I get this. I could do that. Then I could even do, I could do it this way. 1, 2, 3 matrix. 1, 1. So we get 1, 1, 2, 2, and 3, 3. But then we add here 10 to the negative 16. And then I do 1, negative 1, right? And then from there, well, I should get something out. So I get 1, 2, 3. This is 10 to the negative 16, 0, 0. And now this is a 2 by 2 matrix, right? And so the idea is that we need 2 column vectors to build all of column A, or 2 vectors to build all rows A, right? And the minimal amount of column and row vectors needed to fully build A is called the rank of A. So that's what I mean by rank. It's the minimal amount of column and row vectors needed to fully build the matrix, right? And so what am I saying here? Well, what do we see actually? Well, here we see that we need 2 column vectors. I can't spell columns. Column vectors. We need 2 column vectors. Let's say U1, which has these elements. And we also need U2, which has these elements. Right? In order to build this thing. In order to get all of the columns of A, right? Okay, and that was the other thing we need to do. Well, then again, here in this case, we need 2 row vectors. Let's maybe call it V1. This is 1, 1. And V2, this is negative 1. Right? Or no, my bad. It's in reverse. 1, negative 1. Right? And then from there, what's going to happen? Well, we need these to, again, build all, instead of columns, we're going to put rows. Right? And then further, the minimal amount of row vectors, or column and row vectors, that are needed to build this matrix A is called its rank. So the rank of A. So let's look at some of them. What if we were to find the rank of this particular matrix? Oh, 1, 2, 3, 4, 5, 6. And we're gonna say this rank is 1. How do we know? Well, we did it previously. Right about here. How many column vectors do we have? We have 1. How many row vectors do we have? We have 1. And so my rank here is the minimal of column and row vectors needed. So the minimal is 1, right? Now let's look at something else. What if we get the rank of this thing? So this is 3 plus 10 to the negative 16 and 3 minus 10 to the negative 16, right? And this is equal to 2 because I needed 2 rows and 2 vectors, or 2 rows and 2 columns and 2 rows to do that. Okay, so let's make a statement here. So we say that for, let's say my matrix A is an n by n dimension. Well, its rank is less than or equal to the minimum in between these two. So in English, well, that means, for instance, in the matrices alone, we only have 2 columns. So we will need a maximum of 2 column vectors to build this column space, right? Okay. So say I have an A matrix here, and it goes from M to N. But we're saying my rank at K, my rank at A is some K value that I don't know. Then we can find a bunch of stuff here. We can find U, and my U here is M by K, right? And then we say V. This is N by K, right? So we have to find those 2 things, U and V, such that my A is exactly my U V inverse. Oh, no, not V inverse, V transpose. Okay. So if we look at it storage-wise, so here now we're looking at it storage-wise. Well, here we see that A is, if we count the number of flops, it's M by N elements, right? If we look at, let's say, U and V, well, we would get M by K plus N by K elements. And here, if k is small, then storing u and v makes more sense. Or no, this is k, I'm assuming. Okay, so we're saying it makes more sense to store u and v in terms of a, or for a, when k is very small. Now, what about something like mathvex and operation counts? So it's been a while since we've done that. So let me do a bit of operation counts. So what is this thing? Well, let's say I have a vector x. It goes all the way to n. And I'm here to ask ax, or a, and this has m by 2n minus 1 operations, right? And if k is small, then it's u. Okay, let me just do this real quick. Well, we have this for ax, right? Well, what if we now change it to uv transpose? Well, now what do we get? Well, here we get k 2n minus 1 plus 2k minus k 2n minus 1 plus m 2k plus 1. Or I'm kidding, minus 1, my bad. Right? So those are the number of operations. And if k is small, well then uvtx is cheaper. So the number of operations are less. And so a lot of matrices are not low rank or have k small, right? But we could be, but these could be approximated by low rank matrices, right? So they can just be approximated here. So let's say, for example, well here we're given this matrix 1, 2, 3 plus 10 to the negative 16. 1, 2, 3 minus 10 to the negative 16. Here I have this matrix, right? And then I do a low rank approximation, right? Then I have, what's this? 0, 0, or no. Because I could simplify this. We have 0, 0, 1. And then we have 1, negative 1 for my row vector. And then we could approximate it to this thing again. So who cares if 10 to the 16th is small? Like, we just don't care pretty much. Yeah. And now I get back to this thing, which again is an approximation with error. This is an approximation with error. And the error is what? 10 to the negative 16, which is not even that bad. So overall, low rank approximations are great. Now, how do we get these low rank approximations? That's the next question. So how do we get low rank approximations. Also because it's faster. It's also one of the reasons. Well, one of the techniques that we could use is SVD, or singular value decomposition. Now here's where I talk about this. And what is this basically? Well, this is given some U, some S, and some V. This will output me. So this is how we do it in MATLAB. We get the SVD, or the singular value decomposition of some matrix A, right? And this is basically some matrix A, which is U, S, V transpose. Here we say that U is an orthonormal. So we did talk about these terms. So it's a matrix, an orthonormal matrix, such that, well, U, if you were to multiply it to transpose, then it's just the identity. So that's what orthonormal means. Okay, so the columns of U consists of the basis of the column space of A, right? So what does that mean? Well, here we say that, okay, so we have U, an orthonormal matrix. We have S. What was this? Okay, let me just write this other one maybe. Here we say that the columns of V consists of the basis of the row space of A. Right? We'll see how that works in depth. Here we say that S consists of the singular values of A. So here we say S. Right? What do we mean when we say singular? It's actually a diagonal matrix where the entries are descending order and show the importance of the respective column and row basis, right? So if we were to kind of go back, actually no, I can't see it. Did I talk about basis in any way? I only used it for like building and stuff. I never really talked about basis. Okay, but here it says S consists of the singular values of A. And here we say that it is a diagonal matrix. So when we say diagonal matrix, there are values in the diagonal. And we're saying that entries are basically in descending order, right? They're in descending order. And they also show the importance of respective column and row bases. So we're gonna just dissect these in a bit. So importance of respective row and column bases. So how exactly does this work, right? Um, let's say if my A matrix is with dimensions, let's say m by n. My V is also a matrix, but this matrix is also m by n. And then we say here that my S is m by n. Hope I'm not messing anything up. And lastly, my V is n by n. So this is a square matrix, right? Well, okay, what do we see? Well, here we see that, oh, okay. Is this right? Oh, this is m by m, my bad. See, there's the error. So this one's m. That way this have to cancel, and then that's m by n. And then we should get this m by n. So here, this is where we decompose our matrix. We decompose it into three matrices, actually. V being the orthonormal matrix, S being the matrix that's diagonal, and it consists of singular values of A, entries in descending order, and show importance of respective row and column basis. And lastly, V, or specifically its columns, consists of the basis of the row space of A. So that's the general idea of this singular value decomposition. Let's move into QR decomposition. And QR decomposition, well, we just, in code, we just do Q and R, and then we put it, there's a built-in function in MATLAB. So I'm actually taking this course in MATLAB. We got QR of A. We say A is equal to QR. This is in mathematical form. So again, we're decomposing this matrix, right? So Q here is again an orthonormal matrix. So again, what do we mean when we say orthonormal? Well, we mean that my Q as well as my Q transpose is just equal to its identity matrix, right? And so the columns of Q consists of the basis of the column space of A. So let me just write that. We're going to say columns of Q consists of basis of column space of A. Right? We're going to say R is an upper triangular matrix. Consisting of linear combination coefficients to rebuild A. So this is just basically another way to decompose our A matrix, right? Okay. I don't have examples for now. I'm gonna talk about more of these in depth at some point. But here, this is just a brief introduction of what these decompositions are. This is just an introduction to my scientific computing, so I'm not expecting too much in-depth explanation of each kinds of decomposition. So this is really just a brief overview of what decompositions are there um, that we could use to make our algorithms more efficient. Because at the end of the day, well, data is just a matrix, right? We can identify them or we can classify them as matrices and vectors. That's the basics. Okay, let's give an example. So we say that if I have a matrix A, this is a square matrix, n by n, and the rank of this matrix is just n. So meaning we need n columns and n rows. And so from there, oh, there we go. We have a um yeah, we have a QR decomposition here. So let me quickly do this really. Yeah, let me do this real quick. So I'm gonna say my A matrix, right, is going to be decomposed to Q and R matrix. And so I have my Q, this goes from Q1, Q2, all the way to Qn, right? So I think that's what the Q meant. It's an orthonormal matrix, and its columns of Q consists of bases of column space of A. Okay. And then from there, now let's see. We have R. So R here is just going from, well, here we say R is an upper triangular matrix consisting of linear combination coefficients to rebuild A. So this is basically an upper triangular matrix. Let's go all the way to N. R12 all the way to R1N, 0, right? So we decompose them to Q and R matrices. And then we solve them. So we would get something like this. We would get R11Q1, R12Q2. Oh no, my bad. R11Q1 plus R22Q2. And then I go all the way and I decompose it. Well, I get the summation of, let's say it goes to N, J starts at 1. Here I have my R and J. This just goes to N and Q, J. And then, well, this is basically just equal to my matrix A, that whole thing. And so, well, yeah, that's how we decompose it. And the idea being it's quicker, right? Okay. Let's try one more of these. Let's see. So let's say for A is an element of all real numbers, and its dimensions are, now let's be a bit more general, m by n. And here we say that if my m is less than n, and my rank the rank of my matrix A is, let's say, some value k. I don't know what that is. Well, then we just say that A is equal to QR. So here we decompose it. We go Q1, Q2, all the way to Qn, right? Or actually, no, in this case, it's K. QK, so not Qn. Okay, I'm gonna go into more depth with these because I immediately went into something general. Yeah, I'm gonna explore more of these decompositions. You have R11, R12, uh, R all the way to R1, okay? So let me fix my handwriting. Okay. And then I have R22. This is all the way to RKK. I go down here. Well, this is sure. R2K, I go down. These are zeros, right? This is an upper triangular matrix. So that's my R1, right? And then I continue from here. So here I have RK, K plus 1, right? Here I have R2, and then this is K plus 1, and this is R1, K plus 1. And then from here, will I go all the way to N? R1N to be specific. This is R2N. And then I go all the way to NN, right? And this is now my R2. So here I kind of decomposed it, right? So I decomposed it. Oh, this is not, my bad, this is not N, this is K. I picked some K value so that I'll be able to decompose this thing, right? And from there, well, what can we zoom out on? Okay, and from there, well, what can we say? So what can we say about it? Well, from here, we can say that, so with Q sub J is an element of, oh, I'm talking about this one. So this is an element of all real numbers M, with J going from 1 all the way to K. So I'm talking about this one here. Let me just put this up. And then this decomposition here, right? What is this? Well, we have, so this is a bit interesting because now I've decomposed it into into three matrices, in fact. So what basically happened in these decomposition, well, we have A is Q, and then I decomposed it to R1. My R, I decomposed it to R sub 1 and R sub 2. And then from here, well, I can say Q R sub 1 is just the identity of my R sub 1 inverse R sub 2, right? So what happened here? Well, I've just added these two, right? And then what else? Well, this is basically equal to my A. Uh, okay, I can't read that notation. Um, well, basically my A. Okay, I'm not gonna bother doing that. But basically, huh, now I'm left with my inverse and then my identity times my R sub 2. Um, yeah. So I'm basically left with that. So I basically stored the original, right? So this is a bit smart if we think about it, because I did QR, and then instead of QR sub 1, I just did A, right? So these are other techniques on how to make algorithms more quicker, I guess. And there's actually a name for this, and we call this an interpolative decomposition, right? That's what we call that. Uh, okay. And so the idea is that, well, we can store matrix A typically through a function, right? Okay, actually, I'm just going to show the notation. The notation is basically like this, something like that. Let me rewrite it. Yeah, it's a weird notation that I've just. But the idea is basically we're storing A as a function of something. Let me see. Yeah, so we can store that particular A with the weird notation, typically through one function. Uh, and then X and Y vectors in a lot of situations. But we set it to the first K columns. So do we think these columns are always the most important? Well, no, sometimes they are useless. And so we permute columns, column pivotal QR. And so what does that mean? Well, we can actually pivot these. And so, okay, let me just, and and then an X and Y vectors in a lot of situations, but we set it to the first K columns. Okay, so then we do a column pivoted QR. And so what does this mean? Well, this just means that I store my Q, R, and my P in here. So I add a permutation. So that's A P equals Q R. And this basically pivots column such that the important columns are in front. Right? Okay, that's it for this video. I know I went through a lot of general stuff, but the idea is that there are certain algorithms and lower rank approximations. This is really just for intuition purposes. Um, there are tons of decompositions that we can use to make our lives easier. And what I mean by make lives easier, I mean making our algorithms more faster. So yeah, I hope you guys enjoyed, and I'll see you all in the next one.